All right, so finally got around to making this video. So this one's going to be how to solve this system of beams that we have here. So at the end of the day, this is really no different than solving a problem that has only one beam. It's just that you're doing two of those problems at once, okay? So we're going to see how this works. So the statement of the problem says, consider two horizontal beams pictured to the right. The beams have known mass M1 and M2 and lengths L1 and L2. Solve for the X and Y components of the forces M1 and M2 act on the wall, the forces in the pin connecting them, and then this is the way that I'm going to denote what these forces are. Okay, so the first thing that we need to do here, actually, or one of the first things that we can do, is determine some angle, because we're not told the angle in the problem at all, and so we actually have to find that ourselves. So I'm going to define this angle right here, call this angle theta, and theta we can find by labeling L1 and L2. So we know that cosine of theta is going to be equal to L1 divided by L2. So if we're solving a problem, we can actually just stop here. We have theta now, okay? And we could also say that we could use this angle phi as well. We could say that the sine of phi is going to be equal to L1 over L2. Okay, so we can just use this theta and this phi now. We've defined it. Okay, so I'm just going to do that from now on instead of plugging back in L1 and L2 here. Okay, so the next thing that we can do now that we have this angle is draw our free body diagrams. So here's going to be L1, and then this is going to be L2. Okay, and so basically, we're just doing exactly the same thing that we did with the other problems. So if we're looking at the bottom one is 2. So this is mass M1, and this is going to be mass M2. So this one has some force acting down at the center of mass. This is going to be M2G. And then we have the force in the wall here. So this is what I called F2Y. And then we can choose directions for this. So this is going to be F2x. Now, we really don't know what the direction these forces are, but we're just going to make a choice. And as long as we make our choices and we're consistent with our coordinate systems, we'll get the right answer. You might find that there's a negative sign somewhere that comes out if we plug some numbers in here, but that's actually not really important for the way that we're defining these things. We just need to pick something and then set our equations up, and then if we find a negative sign in the end, that just means that the forces were pointing the opposite direction as the direction that we drew. Okay, so as long as you're consistent, it's not a problem. Okay, so the forces that 1 act on 2 here, this is going to be the force 1 acts on 2 in the y direction, and then this is going to be the force 1 acts on 2 in the x direction. Okay. We do the same thing for this one. So we're going to draw, here's our force F1y, have a force F2y, okay? We have some force of gravity acting at the center, so this is going to be M1G. Okay, so I mislabeled one of my indices here, so this should be an F1y, okay, F1y. And then this force that 2 acts on 1 needs to be equal and opposite. This is a matter of Newton's third law. So the force that this one is going to act on this one is going to be like this. So this is going to be F21x, and then this is going to be F21y. Okay, so we can actually see if we're looking at a free body diagram, there's a little bit of a problem here with the choice that I made, and it's okay if you stop here and you see that to change it. So what I'm seeing here that's a problem comes to the fact that when I'm looking at my forces in x, both of them are to the left, right? And realistically, that's not going to happen. So one of these has to be the wrong direction, and the one that's actually the wrong direction here is going to be this one. Okay, so I'm going to take this one, I'm going to flip it over, okay? And when I say wrong, like I use wrong in quotation marks, because like I said, you could solve the problem exactly the way that I had it. It just means that you're going to pick up a negative sign in the answer that you're getting, which means that one of the forces It's just the opposite way as the way that you drew it. Okay, but if you catch that early on, sometimes it's easier to just do it like that. Now, this one seems to make sense. The y direction makes sense on this one because at the end of the day, this is supporting this. It's holding it up, right? And the x direction also seems to somewhat make sense because, well, actually, the x direction, it would really kind of depend on the parameters here, what the angle is and what the mass is. So we kind of have to make a guess at this point. But if you, like I said, if you see that they have a situation where just by looking at the free body diagram, it's unbalanced, that means you can flip one of them, and then it'll at least make a little bit more sense then. Okay. So now the next thing that we want to do is we want to sum our forces and our torques, right? So this is the way we do all of these problems. Sum of forces in the x direction is going to be equal to something. So in this particular case for M1, this is going to be the F1x minus F21x, okay? And then this is going to be equal to 0, okay? The next one we have sum of the forces in the y direction. This one says that F1y, and I should define a coordinate system here just to be very explicit. So here's the coordinate system I'm going to be using. F1y plus F21y minus M1g is going to be equal to 0. And then we can sum our torques. So sum our torques. Now, we need to make a choice for where we're summing the torques about. And we have a couple of options for how we're going to do this because there's not really a best option per se. Because we don't have a point that will eliminate more than 2 forces, right? So I could pick this point right here, or I could pick this point right here. And that would eliminate 2, but that's the best that I can do, right? So what I'm going to do here is I'm just going to pick the one on the left, because that's the point it's actually going to rotate about. Why not? So this is going to be equal to this torque here from M1G. So I want to kind of pause for a second and talk about the way that I defined the cross product in the last video and how I can use that here actually. So we had those 2 definitions. We had torque. We have what we're doing here is we're doing torque is equal to R cross F. Okay, and this cross product can be written 2 ways. This can be equal to the magnitude of R times the magnitude of F times the sine of the angle between them times n hat, or in Cartesian coordinates, this would be Rx Fy minus Ry Fx times n hat. Okay. Now, looking at this, the R vector is explicitly in the y direction, or explicitly in the x direction, right? It doesn't have a y component. So this right here is going to give me 0, right? Because Ry is 0. So that's 0. So really what I have here is just Rx times Fy. Okay. So looking at this here, Fy for gravity is just going to be minus mg because it's going to be going down. And so this says that this is going to be L divided by 2 times m1g, right? Same thing that we would get if we thought about this in terms of the angle. Okay, that's important that we get the same thing. And this one's going to be minus because this is going to go in the clockwise direction. Now when we're looking at the next one, this one's going to be plus L times F21y. Okay, that's equal to 0. Okay, so we have 3 equations from this one, and we could actually find more if we wanted to because we could sum our torques about a different point, but I'm not going to worry too much about that. So next thing that we can do is look at M2. Okay, so for M2, what we can do is exactly the same thing that we did before. We're going to sum our forces in the x direction. This is going to be equal to F12x minus F2x is equal to 0. Sum of forces in the y direction is going to be equal to F2y minus f2g plus, this is also minus, this is minus f12, behind my head here for a second, minus f12y, okay? Now, next thing we're going to do, sum our torques. Sum our torques. I'm going to do this about this point. And this is where we're getting a little bit more complicated because now this one's at some angle, right? So remember, I defined this angle right here to be theta, okay? So what we can do is if we're going to sum our torques about this point. This is some distance L divided by 2. And again, let's kind of do this in terms of the way that I did this here, right? So the way that I did this here was to say that this was going to be Rx Fy minus Ry Fx. So Rx here is going to be L over 2 times cosine of theta, and Ry is going to be right here. So this is going to be L over 2 times sine of theta. So now we want to sum our torques. So we're going to write the sum of the torque is going to be equal to, and let's write this kind of term by term here because I'm going to do this kind of in a special way to show you that these two definitions of the cross product are the same. So this is going to be the torque from M2 plus the torque from F12y plus the torque from F12 in x, right? Because all three of these forces are going to impart some torque here, and we just need to evaluate them term by term. Okay. So using the equation that we had here for torque is equal to R cross F is equal to Rx times Fy minus Ry times Fx times n hat. Okay. We can see then that really what we're going to have for this first one, the torque from M2, we know that there is no component of gravity that's going to be in the x direction, right? So for the force of M2, this component right here is going to be 0, okay? So what we have is just Rx times Fy. Well, Rx is going to be, this is going to be equal to L divided by 2 times cosine of theta times our Fy, which is going to be M2G. And we have a negative sign because it's pointing down, right? We follow the same argument for F12y. This is going to be plus L over 2 times, sorry, this is L. So this is going to be L times cosine of theta times F12y in the negative direction. Again, because we chose this to be pointing down, and that's going to be negative relative to the coordinate system that we have. Okay. So the last one we have is we have this F12x. Well, this one's a little bit different, right? Because for F12x, this is going to be, again, Rx Fy minus Ry Fx, and the force is only in the x direction. So this term for this one is 0, and now we just have minus Ry. So Ry for this big triangle here is going to be L. This is going to be L times sine of theta times the force in the x direction, where this force in the x direction is just going to be F12x times F12x. Okay, and that's equal to 0. Okay, so at the end of the day, when we're looking at this problem, and we're going to come back and talk about this for a second, it's not really any more complicated than the other problems that we have aside from the algebra. And I'm not even going to bother going through the algebra here because it would end up being kind of messy and it would take a while. But it's 6 equations, 6 unknowns. We don't know f1x, we don't know f21x, we don't know f1y, we don't know f21y, we don't know what, let's see, what else don't we know? We don't know f2x and f2y, so we don't know f2x, and we don't know f2y. So there's 6 equations and 6 unknowns in the end. Okay, and you can. At this point, I would actually, if I had to solve this, I would be tempted to do it with a computer and use some linear algebra to do this rather than doing it by hand. Okay, but like I promised, I want to come back to the way that I calculate the cross product here, because if you look at this, you say, hold on a second. You have a cosine of theta in this one. You have a cosine of theta in that one. You have a sine of theta in that one. Isn't the torque equal to R cross F, which is going to be equal to the magnitude of R times the magnitude of F times sine of theta? Where did this cosine of theta come from? Well, we'd actually find the same thing. So let me draw the diagram again. We'd find the same thing if we use this formula. So here's the angle of theta. Here is this force F, F sub G that's acting on this. So this is going to be M2G. And then this was R, right? So what happens if we use this formula instead? Well, we need to be really careful here, because the angle that we're really interested in is the angle in between our R vector and our F vector, okay? And that angle right here is actually this angle phi, where phi is going to be equal to 90 minus theta. So really, we're not talking about theta here, we're talking about phi, okay? So you have to be really careful when you're using these equations, when you say, okay, well, what is the torque? This theta here is not always going to be the same as the theta you have in the problem. They're different. And you have to identify, when you're drawing your pictures and you're setting up your diagram, what's the meaning of theta for the cross product, and what's the meaning of theta in the problem that you have. So if we have sine of phi, this is going to be equal to sine of 90 minus theta, which is going to be equal to cosine of theta. Okay, so even doing it this way, we end up seeing the same thing, as we should if the physics is true. Okay, so that's going to be it for this video. I have one more that I'm going to be working on, and then that's going to be it for the videos that I'm working on tonight. All right, take it easy, guys.